Okay, imagine this. You're looking at the space station, right? But forget those familiar cramped metal tubes we always see. Picture something huge, really expansive, like a habitat so big it feels less like a ship and more, well, more like a proper home away from home. Maybe even multiple stories right there in orbit or, standing on the moon. And the craziest part, it got there packed tiny, folded up, and then just inflated. Sort of like a giant high-tech bouncy castle for astronauts.
Yeah, it does sound a bit contradictory, doesn't it? You hear inflatable and space habitats together, and you think, wait, how does that work? Especially with, the vacuum, all the hazards out there. But these structures, or maybe more accurately, expandable habitats, they're really poised to be one of the biggest leaks in space exploration tech, maybe since the rocket itself.
Totally agree. And that's exactly what we're diving into today. We've got a stack of sources here, everything from discussions around actual videos of these things being burst tested to articles covering the big picture,
Yeah.
and even a really dense, detailed techno paper digging into like the nitty-gritty of designing and certifying one for the moon. It's all about how we shift from rigid metal boxes to using these soft, super strong fabrics to build our new homes out there.
Right. And our mission for this deep dive is basically to take all these different angles, the big vision, the tough realities, the hardcore engineering, and kind of synthesize it all. We need to really get our heads around the potential inflatables unlock, but also grapple with the unique, pretty formidable challenges they face, and explore the super clever ways engineers are combining advanced materials and integrated tech to make them safe, reliable, and honestly, even comfortable places to live and work.
And for you listening, why should you care about this? Well, because this isn't just, sci-fi anymore. This tech is genuinely key to doing the big things: large commercial space stations, sustainable moon bases with Artemis, eventually sending crews to Mars. It changes the game because it tackles one of the biggest bottlenecks in space travel: launch volume. Getting big things into space is hard and expensive. This could make it much easier, could change everything. Okay, so let's unpack this. Where do we start? The big picture. The promise of inflatables.
Sounds good. So at its heart, the promise of these expandable habitats comes down to how different they are from traditional spacecraft structures, the rigid ones, usually aluminum alloys, maybe composites. An expandable habitat, it travels folded up, super compact. Then, once it's in space, or say on the moon, it gets expanded to its full size.
That's the high package to deployed volume ratio thing
Yeah.
they talk about, right? Like the ultimate space IKEA, but instead of an Allen wrench, you just add air.
Pretty much, yeah. And that ratio is incredibly valuable. Launch vehicles, even the big ones, they have really strict limits, not just mass, but also the physical space inside the fairing, the nose cone. So if you're sending stuff to the moon, maybe with the CLPS program, the Commercial Lunar Payload Services, or an HLS lander, you might be looking at payloads around, say, 3,600 kilograms for a standard Blue Moon lander from Blue Origin, or maybe up to 6,500 kilograms for bigger version. But a rigid habitat concept mentioned in one source came in at 5,649 kilograms. That's a big chunk of your capacity.
Wow, so the inflatable route potentially lets you pack way more living space or lab space into that same weight and volume limit for launch.
Exactly. You launch a relatively small, dense package and end up with a much, much larger structure once deployed. You get dramatically more usable volume for potentially less launch mass.
That's a huge win for cost, for mission planning, for everything, really.
It really is. And the benefits might go beyond just launch. The technical paper points out a few other potential upsides. Theoretically, because they start compact, maybe some designs could be deflated, moved, and reinflated. That adds complexity, of course, but it's an interesting idea. They might also handle dynamic loads differently, potentially better in some cases. Unlike a rigid structure that can resonate, the internal pressure changes how an inflatable absorbs and distributes forces, maybe making it more resilient to certain vibrations or impacts during maneuvers.
And you mentioned something about thermal advantages
Yeah.
because of the large surface area. How's that work?
Right. Well, with the bigger surface, you've got more area to radiate heat away into space. Or you can use specialized coatings and the insulation layers to manage solar heating more effectively. Compared to a smaller rigid module with the same internal volume, a large inflatable cylinder just gives you more options, more surface area to play with for thermal control strategies.
Makes sense. So, okay, they're great for habitats, obviously. But this inflatable tech, it's not just for living quarters, is it? The sources mentioned other uses.
Oh, definitely not. The core idea, launch small, deploy big, it's useful elsewhere. Like inflatable heat shields are a really hot area of research. They could allow much heavier payloads to re-enter atmospheres safely because they deploy into this huge drag surface, slowing things down and spreading out the heat.
Yeah, I can picture that. Launching a heat shield, folded like an umbrella, then it pops open to this massive size before hitting the atmosphere. Way better than launching a giant rigid cone.
Exactly. And inflatable antennas, they're already kind of revolutionizing things. You launch them tiny, but they unfurl into these enormous dishes, way bigger than you could ever launch rigidly. That means much better signal for deep space comms.
Right. You mentioned airlocks, too.
Yeah, inflatable airlocks are another concept. Super important for spacewalks, EVAs, or just moving between pressurized areas. An inflatable one could save a ton of internal volume when it's not being used.
It's easy to think this is all, like, brand new tech, cutting edge.
Ugh.
But the sources point out this idea has actually been around for a while. A long while.
Oh, absolutely. It goes back further than you might think. Werner von Braun himself, the rocket guy, he was sketching out ideas for inflatable sections way back in 1952 for his big rotating wheel space station design.
No way, 1952. Before Sputnik, even.
Yep. He saw the potential for soft, expandable parts even then. And then, in the 60s, Goodyear Aerospace did a ton of work. They teamed up with NASA Langley, did a lot of research, built full-scale test articles. They were looking at lunar habitats, inflatable airlocks, really tackling the basic engineering of making these multi-layer fabric structures tough enough for space way back then.
But the first actual human-rated inflatable in space?
Yeah.
That was Russian, right? The Volga airlock?
That's the one. 1965, Voskhod 2 mission. They kind of needed it because they couldn't depressurize the main capsule for a spacewalk without risking the electronics.
Yeah.
So necessity being the mother of invention, they tacked on this external fabric airlock and inflated it, and it worked. Alexei Leonov took the first ever spacewalk through it.
Wow. The first person to float free in space stepped out through an inflatable door. That's amazing.
It is pretty cool. Although, the Volga did have some issues, apparently problems sealing properly. And the Soviets ended up shifting strategy later, just depressurizing spacecraft sections instead. So the inflatable airlock idea got shelved for a bit.
But NASA picked it up again in the 90s with Transhab.
Right, Transhab was a big deal. It was designed initially as a habitat for a Mars transit mission, giving the crew lots of room for that long trip. It was also pitched for the ISS. NASA put a lot of effort into it. Langley and other centers did tons of research, hydrostatic tests, vacuum deployment tests on large sections. They really developed the thinking around the multi-layer shell structure you need.
And that work didn't just disappear, right? Bigelow Aerospace licensed those patents.
Exactly. And Bigelow really deserves credit for pushing inflatable tech back into the spotlight and crucially proving it works in orbit. Their beam module, the Bigelow Expandable Activity Module on the ISS, that's the key demonstrator.
Launched back in April 2016 and wasn't supposed to be just a temporary test, like 2 years maybe?
That was the original plan, yeah. Just attach it, see how it holds up to the space environment, radiation, debris, temperature swings, the whole 9 yards. But honestly, it performed way better than expected. So NASA just kept it. It's still attached now, almost 8 years later.
8 years. And it's not just sitting there empty. They're using it for storage now, right after it finished its main tests.
Yep. It added over 500 cubic feet of usable volume to the station. That kind of longevity, that continued usefulness, is just massive validation for the concept in the real, incredibly tough environment of space.
It really is. And the testing hasn't stopped. That burst test video discussion you mentioned sounds intense.
Oh, it's compelling stuff. Seeing a full-scale habitat module inflated until it finally ruptures, it really demonstrates the incredible strength these things have. They pushed that test article to 75 psi.
75 psi. And normal pressure inside is what, 14.7 sea level pressure?
Exactly. So 75 psi is 5 times the normal operating pressure. That's a huge safety margin built in.
5 times.
Yeah.
Okay, that really underlines the engineering focus on safety.
It does. It shows that under normal conditions, the structure is way, way within its limits. And there was an interesting comment in that discussion, too, about how Bigelow's earlier tests apparently always showed the rupture happening at a seam.
Ah, so not the fabric itself tearing, but the joins.
Right. Which tells you that while the materials are incredibly strong, how you join them, the seams, the connections, those are the critical points. Design, quality control and manufacturing, thorough testing of those joints, Absolutely vital. The strength isn't just the material, it's how it's assembled.
And it's not just U.S. companies anymore, is it? China tested one recently.
Yeah, they quietly tested their first inflatable module, which just shows this tech is being taken seriously globally as a real option for building future space infrastructure.
And looking forward, Sierra Space has their life concept, large, integrated, flexible environment.
Right. Their vision is pretty ambitious, talking about really changing how people live and work off Earth. They throw around some huge numbers for potential volume. I think their materials mention concepts getting up to maybe 5,000 cubic meters eventually. But the first one they're planning is like a three-story structure, about 27 feet across, designed to sleep four astronauts comfortably, plenty of room for science gear, exercise, medical stuff, even an astro garden to grow fresh food.
3 stories. And gardening.
Yeah.
In space. That really does feel like a different world compared to, the current station modules.
It leverages that core inflatable advantage,
Yeah.
right? Getting way more volume than you could ever launch rigid. Concepts like life, they're seen as stepping stones towards future commercial stations like Orbital Reef, which Sierra Space is involved in with Blue Origin, or bigger, more comfortable habitats for the Moon or Mars.
So you put it all together. The launch efficiency, the different applications, the history, Beam proving it works, the tough testing, these ambitious future plans like life. It really hammers home that inflatables aren't just theory anymore. They're real, they're being actively developed, and they seem pretty fundamental to getting bigger, more capable, more livable spaces off Earth.
Absolutely, and it's big, but space is incredibly hostile. And an inflatable structure, even one that's super strong when pressurized, it faces a really unique set of challenges engineers have to solve.
Yeah, that's the instinctive reaction, isn't it? It feels vulnerable. What are the biggest threats it has to deal with?
Okay, well, start with the most basic one, vacuum. Just holding 14.7 psi sea level pressure inside when there's basically nothing outside.
Okay.
That requires a really good gas retention layer, a bladder essentially. It has to be incredibly leak-proof, stopping gas from slowly diffusing out over years, many decades. That pressure difference is constant, relentless.
Okay, holding the air in, check. What about physical threats? The one everyone asks about. Micrometeoroids and orbital debris, MMOD. Isn't an inflatable just going to get popped like a balloon?
That's the natural assumption, but that's where the really clever engineering comes in. These aren't simple balloons, remember. They use multi-layered protection. Think of it like high-tech body armor woven right into the fabric shell. The outer layers often act like Whipple shields. That's the concept used on the ISS too. When a tiny particle hits the outer layer at insane speed, it doesn't just punch a hole. The impact shatters the particle, spreads the energy out over the next layers. It can even vaporize it. Then the layers underneath are designed to catch those fragments, absorb the plasma cloud.
So it's not about stopping it dead, it's about breaking it up and managing the hit.
Exactly. And the materials are key. High-strength fabrics, often with a ripstop weave, so if a tiny puncture does happen, it doesn't easily tear bigger. Specific sewing techniques help too.
And that comment about impacts at speed causing vaporization. That's wild. The speed actually helps the shield work.
In a way, yes. At those crazy orbital speeds, the kinetic energy is so high, the impact is almost like a tiny explosion. The particle turns to gas or plasma instantly. The challenge then is containing that blast, which the layers are designed to do.
And Beam just sitting up there on the ISS for 8 years without getting taken out by debris is...
Well, it's pretty compelling proof that the shielding actually works in a real debris-filled environment.
It's huge validation. No mission-ending MOD hits. And importantly, if a small manageable leak does occur, repairs are possible. The sources mentioned patching from the inside, using the internal pressure to kind of push the patch against the hole. Reminds you of that ISS leak back in 2018, right?
Yep.
The crew used, what was it, Captain tape first, then duct tape, eventually a proper patch with sealant.
Yeah, they basically MacGyvered it from the inside.
Right. And it worked. It shows that soft goods can be repaired in space, even with relatively simple means. That's a critical capability. Okay, so MMOG is manageable with smart layers and repair plans. What about radiation? That's always a huge concern, especially outside Earth's magnetic shield, like on the moon.
Radiation is definitely a primary hazard for long trips beyond LEO, low Earth orbit. You've got the constant galactic cosmic rays, GCRs, these super high energy particles from deep space. Then you have solar particle events, SPEs, unpredictable bursts of radiation from the sun. And potentially neutron radiation too, which can happen when GCRs or SPEs smack into the habitat walls, especially denser materials like metal.
Wait, so a metal habitat could actually create more radiation inside, secondary radiation?
That's a known issue, yeah. So the material choices for the inflatable layers are really important for shielding. Things like polyethylene, Kevlar, Vectran, they have some natural ability to block certain radiation types. Polyethylene's pretty good with protons, which are a big part of SPEs.
The tech paper also mentioned using natural shielding, like on the moon.
Right. You could potentially put a base inside a lava tube or bury the habitat under meters of lunar regolith, the moon dirt. Both offer excellent shielding. Regolith is very effective, but there are big downsides, especially early on. We don't know much about how stable lunar lava tubes really are, and burying a habitat that takes heavy equipment, a lot of astronaut time and effort, and kicks up tons of that nasty lunar dust. Very challenging for initial crews.
So natural shielding is maybe a long-term goal, but not the first step.
Probably not for the first deployed habitat, no. For immediate protection against those intense, sudden solar particle events, habitats will need dedicated storm shelters inside, heavily shielded areas. At that old TransHab design, for example, its SPE shelter was something like 40% of its total wet mass. A lot of that was water, which is a great shield, but it shows you the sheer amount of mass needed just for SPE protection.
40% just for the shelter. Wow.
Yeah.
Okay, that really drives home the radiation challenge. And lunar dust, you mentioned it briefly. Sounds like bad news.
It really is. Lunar dust isn't like dust on Earth. It's not been weathered by wind and water, so it's incredibly sharp, like microscopic shards of glass. And it gets electrostatically charged by the sun, so it sticks to everything. It's abrasive. It gets into seals, mechanisms. The paper specifically flagged concerns about it potentially jamming up airtight zippers if those were used in designs. That would be critical.
Okay, so keeping dust out is paramount. How do you do that with an inflatable?
The main strategy is multi-chamber airlocks. You have several stages. Astronauts take off their dusty suits in an outer chamber, maybe clean them off, then move to an inner chamber before finally entering the main habitat. It's designed to trap the dust progressively. That LEIA airlock concept in the paper, lightweight external inflatable airlock. That's exactly what it is, a multi-chamber inflatable designed for lunar dust mitigation.
And inside the habitat itself, any special precautions?
For rigid parts, like maybe floor panels or connection points inside the airlock, they're looking at ceramic coatings. Much tougher, more resistant to that abrasive dust than standard surfaces.
So again, it's layers of solutions. Materials, smart airlock design, surface treatments, any other environmental factors to worry about?
Well, you have the thermal extremes, baking hot in sunlight, freezing cold in shadow. But like we said, the large surface area can actually help manage that with insulation, MLI, and coatings.
Right. And none of this works: the bladder, the shields, the life support, the heating, the cooling, inflation itself, without power, right?
Power is absolutely essential, yeah. On the moon, you could use solar arrays, but then you need hefty batteries for the 2-week lunar night. Or if you're in a permanently shadowed crater for radiation reasons, though those places are incredibly cold. The Artemis program is also planning for nuclear power sources. Fission surface power could be sited away from the habitat, saving launch mass for the habitat itself. And nuclear gives you constant power day or night, which is a massive plus for a permanent base.
It's just amazing how many things you have to account for. These aren't just passive structures. They're complex, active ecosystems designed to fend off a truly hostile environment.
Exactly. Which brings us right into the engineering heart of it. How do you actually build something this complex out of essentially fabric and flexible materials? It's obviously way more than just a fancy balloon.
Definitely. The core structure, the thing that actually holds the pressure and takes the loads, is that multi-layered shell. The paper broke down the typical layers.
Right. Usually starting from the inside, you've got the bladder, the gas retention layer, just holds the air in. Then maybe a protective liner inside that. Then often multi-layer insulation, MLI, for keeping the temperature stable. Outside that, you get the MMOD protection layers we talked about.
Right.
And then the real backbone, the structural restraint layer.
Restraint layer. That's the strong stuff, the webbing or fabric that stops it from bursting under pressure.
That's the one, made of super high-strength soft goods. And then typically there's an outermost layer, sometimes called an attenuation layer, that provides the final shield against abrasion, radiation, thermal effects, and any MMOD that gets through the first defenses.
And what are those restraint layer materials? Kevlar you mentioned.
Kevlar was used in TransHab, yeah. More recent work, like at NASA Langley, has used Vectran quite a bit. And looking ahead, there's early research into boron nitride nanotubes, BNNT, as a potential game changer.
BNNT. Did we mention that for radiation shielding too? It does both.
Potentially, yeah. BNNTs are incredibly strong. In theory, lab tests show strengths maybe 100 times steel, but way lighter. Plus, they handle heat well and are chemically stable. So the idea is maybe BNNT reinforced fabrics or cords could be the next big thing for structural layers. Still early days, though.
Okay, so you have these super strong fibers or webbings. How do you actually arrange them to form the structure? The paper talked about different architectures.
Yeah, that's a really important design choice. One way is a closed basket weave, like TransHab did. Imagine weaving straps together tightly. It's really robust because if one strap breaks, the friction with its neighbors lets them pick up the load. Great for damage tolerance, very redundant, but
But hard to predict exactly how the load flows.
exactly. Structurally complex, difficult to model perfectly. Another approach is using stitched hoop webbings, like bands running around the structure. Simpler to make, maybe, but the stitches become stress points. Then there's maybe an open mesh grid over a fabric layer, lighter perhaps, but maybe not as tough.
And the paper seemed keen on something called low hoop stress or lobed designs, said they were most mass efficient.
Right. Think about high-altitude balloons or some parachute designs. The main loads are carried along specific tension lines, like cords running lengthwise and hoops running around. The load paths are clearer, more determinate, which makes them easier and model accurately. That can lead to really lightweight designs. The catch is they might be less redundant. If a primary load-bearing cord fails, the load might not redistribute as easily as in a basket weave. Could be catastrophic unless you build in other fail-safes, like backup fabric layers.
So it's all trade-offs. Mass versus robustness versus how easy it is to manufacture and model.
Always trade-offs in engineering, especially here. And adding to the complexity, these soft good materials themselves just behave differently than metals. Engineers have had to learn a whole new set of rules.
How so? What's different?
Well, for one, their load strain behavior isn't linear, especially at first. You know how when you pull a rope, it might stretch easily for a bit before it gets really stiff?
Yeah.
That initial stretch is the fibers kind of straightening out, uncrimping. Once they're aligned, then the material gets stiff. Metals don't really do that in the same way.
And what was that about load history dependence? That sounds...
It is. Basically, the material remembers if it's been stretched before. If you load it up a few times, precondition it, it gets stiffer and behaves more predictably. But if it sits folded up for months during its trip to space, it relaxes, recovers some of that crimp. So its exact stiffness when you inflate it might be different than when it was tested. Makes predicting its behavior and tracking the real loads much harder than with metal.
And the variability. You mentioned the strength can vary a lot.
Hugely. Way more than metals. That NASA Langley testing on Vectran, they found the average breaking strength varied by almost 6% for one type of webbing, up to over 9% for another. And the maximum deviation from the average was 21%.
21%.
Yeah.
And the strength of your main structural material, that's massive uncertainty.
It is. And often, commercial suppliers only guarantee a minimum strength, an S basis value, not the statistically robust A or B basis allowables engineers prefer, which give you high confidence levels. All that uncertainty means designers have to use much bigger safety margins than for metals, just to be sure, which makes the structure heavier than it might theoretically need to be, less efficient.
And then there's creep. The paper called it the silent killer for long missions. What is creep exactly?
Creep is basically the slow, steady stretching of a material over time when it's under a constant load. These polymer materials are viscoelastic. They deform gradually under stress.
Why is that so bad for a habitat meant to last, say, 15 years or more?
Because that slow stretching can eventually lead to failure. It limits the usable lifespan of the structure. And it's really sensitive to how much load the material is carrying. Creep speeds up exponentially as you increase the load relative to the material's ultimate strength. That example in the paper was striking. Vectran webbing loaded to just 50% of its ultimate strength failed from creep in only about a year.
1 year. When you need it to last 15 or more, that's not good.
Not good at all. And it gets worse. Because of those load distribution uncertainties we talked about, if one part of the structure happens to be carrying slightly more load than average, maybe just 5% more than the design intent, its lifespan due to creep could drop dramatically, from years potentially down to months, or even less, depending on the specifics.
So tiny imperfections in how the load is shared could drastically shorten the habitat's life.
That's the major concern. It's a huge challenge for ensuring long-term reliability. Dealing with it means lots of long-term testing, trying to accelerate testing realistically, and ultimately designing the structure so the materials operate at a very low percentage of their ultimate strength. Maybe only 10–20% or even lower to get that 15+ year lifespan, which again adds weight.
These are definitely significant hurdles. But the sources also talked about some really cool technologies being developed to actually make these things work reliably, some integrated right into the fabric.
Yeah, it's not just passive layers anymore. They're building an intelligence capability. The paper categorized them by technology readiness level, TRL, how mature they are. Some are seen as critical, some enhancing, some maybe transformational down the line.
What were some of the critical ones, the must-haves?
Okay, one they highlighted was NFLX Fabric Intelligent Flexible Material Fabric. It's a concept from ILC Dover and NASA Langley, currently around TRL3. The idea is to integrate multiple functions holding air, providing structure, MMOD protection, thermal control, maybe even some radiation shielding into a single advanced fabric system. If you can't do that, you have to add separate layers for each job, which means more mass, more bulk when it's packed. So this integrated approach is key for efficiency.
Got it. The fabric itself does multiple jobs. Smart. What else?
Habitat health accelerometers, basically tiny sensors, accelerometers embedded in the fabric layers. They listen for the high-frequency vibrations caused by an MMOD impact or maybe some other structural event.
Like a microphone to hear if you've been hit?
Kind of, yeah. And using software that knows how the structure should vibrate, they can pinpoint where the impact happened. Crucial information for assessing damage. And this isn't sci-fi, it's TRL9. It's been used on the ISS for monitoring impacts and loads. Vital for knowing the habitat's health, especially since that main structural layer probably isn't easily repairable from the inside.
And they mentioned piezoelectric BNNT fabric as another way to do that.
That's a more futuristic idea, lower TRL. Piezoelectric materials create an electric charge when stressed. So a BNNT fabric might be able to signal an impact electrically, could offer different sensing options.
Okay, what about protecting the habitat when it first lands from rubbing against the abrasive moon surface?
That's the deployable friction barrier, TRL3. It's essentially a protective ground sheet that deploys between the habitat and the surface. Protects the main structure from getting scuffed or torn by sharp rocks or dust as it inflates and settles. Designed to deploy passively, using stored energy, so no complex motors needed.
And BNNT again. You mentioned it for structure and radiation. Other uses.
Potentially BNNT guy lines, TRL2. Given how strong and light BNNT is supposed to be, you could use it for external cables to help anchor or tension the habitat on the surface, like tent lines, or maybe internal ribs. And the neutron shielding is a nice bonus.
And the airlock for dust.
Right. LAA, Lightweight External Inflatable Airlock, TRL2. Taking that multi-chamber dust trap idea and building it as an inflatable structure to save launch volume. Critical for keeping the inside clean on the moon.
Okay, those sound pretty fundamental. What about technologies they called enhancing? Things that make it better but aren't strictly required.
Good examples there, like the Tressellator, TRL4.
Ah, yeah, the thing that builds structures in space.
Exactly. It's a robotic system designed to autonomously manufacture floor joists out of carbon fiber reinforced polymer, CFRP, right there in space or on the moon. Instead of launching bulky pre-made floor sections, you launch spools of carbon fiber and resin, and the robot builds the trusses. Big savings on launch mass and volume. They've already built prototypes strong enough for someone to stand on.
That's brilliant. More structure for less launch weight. What about robots for setup?
That would be assemblers, TRL3, conceptual robots, maybe hexapods that could help put base elements together, move modules around, maybe even configure future lunar cities. Reduces the need for astronauts to do all that heavy, potentially risky EVA work.
And robot swarms. Sound like something out of a movie.
Also, TRL3. The idea is deploying lots of small, autonomous robots for inspection, maybe minor maintenance, monitoring the outside of the habitat. Especially useful if the habitat is uncrewed for periods. They'd coordinate amongst themselves and report back.
So it's really about creating a smart, self-aware, somewhat self-sufficient system, not just a passive shell.
That's the goal, a resilient system. The paper also touched on things like using parts of the landing vehicle for internal flooring, using those ceramic coatings inside, and needing better designs for lifestyle things, good places to attach equipment inside, maybe more integrated health monitoring for the crew themselves.
It's just staggering, the level of detailed engineering needed. From the chemistry of the fibers to the robotics, all to make a fabric structure a viable home.
And all that incredible engineering, all those materials and technologies, they all lead to the final, maybe steepest hurdle. proving it's safe enough for humans. Certification.
Right. Because like you said, the stakes don't get higher. Loss of crew is the ultimate failure. The burden of proof for human-rated has to be immense.
It is. And certifying inflatables is extra tough because, well, the rule book was written for metal cans. There just aren't specific, established standards designed for the weird behaviors, the unique failure modes, the whole multi-layer complexity of these high-strength soft goods in space.
The paper mentioned inheriting a factor of safety FOS of 4 from old airship rules. Why isn't that good enough?
Well, an FOS of 4 sounds great. Design it to handle 4 times the expected load. It builds in a big margin for uncertainty, which you definitely need with soft goods. But it's kind of a blunt instrument. It doesn't really care why you're uncertain. It doesn't specifically target the different risks, creep versus radiation damage versus variability versus seam strength. It's not tailored to the specific design, the specific materials, the specific mission.
And actually measuring the stress in the fabric once it's built and inflated must be way harder than sticking a strain gauge on metal.
Oh, much harder. How do you accurately measure strain inside a complex, flexible, multi-layered fabric structure in space? And getting your computer models to match real-world tests is tough too. The goal is usually within 10% for stress or deflection, which is challenging with materials that vary so much and behave non-linearly.
So if the old rules don't quite fit, how are they tackling certification? The paper talked about a design factor approach.
Yeah, that's the direction things are moving. Instead of one simple factor of safety, they're developing a more detailed, risk-informed design factor. The formula they proposed looks something like: design factor is FOS, LDF, LSF, UF. It breaks down the required safety margin into different components.
Okay, let's unpack that. FOS is still the starting point, the basic factor of safety.
Correct. That's based on how critical the system is, human life support, obviously top criticality, the specific use case, and past experience. The hope is, with better understanding and characterization, maybe that baseline FOS could eventually come down from 4 to maybe 2 or 3, but only because the other factors pick up the slack.
Okay, then LDF and LSF, load and loss factors.
Exactly. These are factors that adjust the safety margin based on specifics. Load factors, LDF, effectively increase the load side of the equation to account for uncertainties there. Things like that inherent material variability, non-uniform loads from how it's built or shaped, dynamic loads during operation.
So if your material strength might be 20% lower than average sometimes, the LDF makes sure you design for that worst case.
Essentially, yes. Or you account for the probability of hitting that weak spot. Loss factors, LSF, conversely, effectively reduce the strength or lifespan side of the equation. They account for degradation over time. Think thermal cycling, UV exposure, radiation damage, damage from folding and unfolding, abrasion, tearing, seam reliability, fatigue from pressure cycles, and of course, creep.
Okay, so you take the baseline FOS, multiply by factors for load uncertainty, divide by factors for strength degradation over time, and that gives a more tailored safety requirement.
That's the core idea. You're explicitly quantifying the risks based on testing and analysis for that specific design in that specific environment. And then there's one more piece, UF, the uncertainty factor.
Uncertainty factor, what's that cover?
This captures the system-level unknowns and your overall confidence in the whole process. How good were your tests? Did you do enough? Were they realistic? Can you actually verify the finished product? How redundant is the structure? Does it leak before it bursts? Can it redistribute load? Can you even repair the main structural layer? Probably not easily, which means you need super high confidence up front. How good were the manufacturing controls? How experienced is the team? And critically, how confident are you in your estimates for all those LDF and LSF factors?
Wow, no. So the design factor isn't just about brute strength. It's about a really deep, documented, justifiable understanding of every single risk and uncertainty for that specific habitat.
Precisely. It forces a rigorous, statistically defensible approach to proving safety, and it relies heavily on testing and advanced modeling.
How does the testing cope with all that variability and weird behavior?
They use what's called a building block approach. Test small material coupons first. Then test representative bits, like seams or joints. Then bigger panels. Then, ideally, a full-scale article. At each step, computer models predict how it should behave based on the smaller tests, and the actual test results are fed back to refine the models. It's iterative.
And planning those tests efficiently.
That's where design of experiments, DOE, comes in. It's a statistical method to figure out which factors, temperature, radiation, folding, whatever, have the biggest impact, and if they interact. Need multiple samples for each test condition. The paper suggested at least 5 to get statistically meaningful results.
And modeling things that are inherently variable and nonlinear, How do computers handle that?
They're increasingly using stochastic or probabilistic methods. Instead of plugging in single average or minimum numbers for strength or stiffness, these models use the statistical distributions of those properties. They run the simulation many times with different variations within those distributions. This gives you not just one answer, but a range of possible outcomes and the probability of failure. NASA Langley's using this for their MASH-AISH airlock model, trying to really bound the uncertainties.
It sounds incredibly thorough. Necessary, obviously, but really complex.
It has to be. The whole point of this detailed framework, the testing, the modeling, the design factor, is to create a standard, trustworthy process for certifying future human-rated inflatables. Beam got certified through a custom process because these standards didn't really exist yet. But the research we're talking about, like in that technical paper, is feeding directly into developing those formal standards we need for the future.
It's just amazing how much deep science and meticulous engineering goes into making sure a fabric structure is actually a safe place for people to live, millions of miles from home. It's that process that turns the exciting idea into something real and reliable.
And that reliability, that certified safety, is absolutely paramount when human lives are involved. There's no room for error.
So this whole deep dive, it's taken us from this almost counterintuitive idea of blowing up habitats in space, all the way through to the nitty-gritty engineering that makes it possible. We've seen the huge potential for creating bigger, better spaces off Earth. We've looked at the gauntlet of challenges they face: vacuum debris, radiation dust, temperature, and we've dug into the sophisticated materials, the smart embedded tech, and the incredibly rigorous certification process needed to make them tough, safe, and long-lasting.
It really is a powerful demonstration of engineering ingenuity, isn't it? Taking these flexible materials and figuring out how to make them not just survive, but thrive in some of the harshest environments imaginable. Proving soft goods can be space tough.
And it really makes those future visions commercial space stations, the Artemis moon base, feel much more tangible. That ability to launch big volumes packed small just changes the whole game for space architecture. Because more volume isn't just storage space. It's room for better labs, proper exercise areas, maybe even some personal space. It's about quality of life for crews spending months, maybe years away from Earth, potentially much closer to life on Earth than being stuck in a tiny can.
Exactly. Volume unlocks capability. It unlocks potential. It's the difference between just enduring a mission and actually living and working productively, maybe even comfortably in space.
It really is. Okay, so let's leave you, our listener, with a thought to mull over based on all this. If these expandable habitats really deliver on their promise of opening up vast new volumes beyond Earth, what does a truly comfortable, spacious home in space actually feel like? How might just the psychology of living somewhere that isn't a cramped metal tube change the whole human experience of being off-world? And what new kinds of work, what new research, what collaborations, maybe even what new ways of just being in space become possible when we're not quite so limited by the size constraints of our rockets anymore? Think about it. What would you do with all that extra room?